case where you have a liquid puddle. So basically, you have a larger droplet. In some cases, we call it as a puddle. In some cases, we call it as a shallow droplet. So these droplets typically have got low contact angles, less than 30 degrees. So they're basically flat droplets. And one of the questions we always have is, what is the height of such a droplet? What is the height of such a droplet? So I'm going to shift to tab. Okay. So basically, the case we are looking at is a puddle. So you've got okay. So you've got a wall, and you've got a droplet which looks like this. Okay. Obviously, I've exaggerated it a bit, but anyway, this is how the droplet looks like. And the idea is that, so for example, if you spill coffee or whatever, if you form a puddle, the puddle, it starts from the contact line in this way, and then it almost approaches kind of an asymptotic length, asymptotic height. And the idea is, what is the height of that droplet? What is the height of that particular thing? And obviously, when you spill coffee, it's sitting there because you've got gravity. Okay, because you've got gravity, and obviously it will have some sort of a contact angle. So if this is your liquid phase, you'll have a sigma LV. Okay, you will have a sigma SV. You got, or SG, whatever you want to call it, and this is sigma SL. So you've got these things happening there. Sigma LV is going all over the droplet. Okay, so technically you will have surface tension in this way as well. So you've got sigma LV here. Okay. The other thing, that obviously you spilt your coffee. It's in the atmospheric pressure. So you've got P gas, which is affecting the whole area. Okay. So technically you've got P gas, which is exerting pressure from all over the place. So this is your P gas. Okay, so this is your P gas. The other thing that you can look at is you have a certain height of the droplet, and this is what we want to find out what that is. So what is the asymptotic height of such a droplet? Okay, what is the asymptotic height of such a droplet? So what we are going to focus on, just this middle region. Okay, we're going to focus just on this middle region, and what we're going to find out is how to calculate such a height. Okay. So if you consider a kind of a cylindrical geometry, so this is the radial direction, this is the axial direction, and we are just looking at this region. So here, the height of the droplet, say the maximum height is h. Okay, and we want to find out what that h is. Okay, so if we look at such a kind of a system, you have the pressure of the gas which is applying on the droplet. You can see that, but you also have the droplet is sitting there. It's not just, the reason it is existing there because it is applying a counter pressure. So you also have some sort of a P puddle or P droplet. I'll just put it as P puddle, which is a function of radius and height. Okay, so you've got the P puddle which is exerting pressure across the droplet, so exerting pressure all over the place. Okay, and this is sitting in this way. Okay, so one of the things, if we start like this, so the first thing we do is we can say force pulling at the contact line. Okay, the force pulling at the contact line is sigma Sg or sigma Sv, that is there. Okay, so this is obviously in one direction. Now the other, signs don't matter as long as we follow some convention. The other thing you can see is you also have a force, the solid liquid force. This was basically the solid gas force, but you'll also have a solid liquid force pulling at the contact line. So solid liquid force pulling at the contact line, if sigma Sg is in that direction, sigma Sl is in this direction. So I'll just, if this is positive, this is negative. As I mentioned, as long as we follow a convention, it doesn't matter. Okay. Then you also have the liquid vapor. So the liquid vapor is the force pulling, again, liquid vapor force pulling at the contact line. So this would be something similar to minus sigma LV. So these are the forces that are acting specifically at the contact line. Okay. Now, if we do if we actually do a pressure balance, if we want to understand what is the pressure and what is the effect of this, so all of these forces must be balanced in accordance to PG and in accordance to what P puddle is doing here. So the first thing we'll try to find out is what is P puddle. Okay. PG is very simple. You will see that immediately coming through. But the most important thing is what is PP, which is a function of R and Z. Now, one way to look at this is, if you want to understand PP, let us understand the force exerted by this pressure. Okay, the force exerted by this pressure, the force exerted by this would be something like pressure into some area. And obviously this is over a certain height Z, and this is over a certain unit width. So I can write the force per unit length as going from 0 to h, integral 0 to h, P puddle dz. Okay? And what I mentioned earlier is we are looking only at the center of the droplet. We are looking basically in the region which is r equal to 0. So this is basically at the point where you have the maximum height, and we want to determine what that maximum height is. So technically P puddle at r equal to 0, kind of a thing we are looking at. So if we look at this P puddle at r equal to 0, we would have to find out what is P puddle in the first place. So P puddle can be written as P puddle RZ can be written as, obviously there is the effect of gas, PG, plus there is also a surface tension force acting on the system. So you'll have some sigma LV times curvature. Okay, that is your pressure force. Plus, obviously, you will also have the effect of the hydrostatic head, so which is basically rho g, something like h minus z, depending upon which point you're looking at what axis you're looking at, you can say that this is something like this. Okay. Now, what we're going to do is we're going to integrate this with respect to z to determine the total force on that system. So I'm just going to go to the next page. Oh, sorry. No. Oh, okay. I'm just going to go previous page plus. Okay, this one. So basically, I can write this as, so force by the puddle is equal to something like, as I mentioned, 0 to h. What happened? Is it? No. It got erased, I think. Okay, fine. Doesn't matter. Okay, so I'm going to write this as force by the puddle is going to be equal to integral 0 to h. Again, probably it's just my bad habit, I think. What do? I go back, is it? Okay. Again, force by the puddle Rz is integral 0 to h, finally P puddle Rz dz. So I'm just going to put this here. So this was like 0 to h. The first thing was you got P gas, okay, plus sigma LV kappa, sigma LV kappa thing, whatever, plus you will have rho g, what was that? I think h minus z dz, something like this. You will get something like that. Okay. Now, if you look at this particular expression here, it talks about sigma LV kappa, and we are looking at only one particular point in the system. So if you're looking at one particular point in the system, I'm mainly worried about what is happening from the P gas side and what is happening at the rho g side. So because I'm looking at only at, and this is at r equal to 0. So if you look at r equal to 0, this will almost become a small term. This is almost negligible. You will get you'll get a very small value here. But the most important terms are these. So if I write this, this becomes 0 to h p gas dz plus you would probably get something like integral 0 to h. So this almost becomes 0 at r equal to 0. So 0 to h rho g h minus z dz. Okay, so this becomes pg, if I apply the limits, it becomes pgh, plus you will get something like rho g h squared, if I just integrate this once, minus you will get rho g z dz, which is z squared by 2. If I apply the limit, this becomes h squared by 2. Okay, so next page. So you would get simply something like the force because of the puddle is equal to something like pg times h plus rho g h squared by 2. Okay, so this is the force exerted by the puddle at that particular point in the center of the domain. Okay, so what we are now going to do is we're going to do the force balance. So the force balance, the full force balance would be something like this. You got the gas, solid gas surface tension minus liquid solid surface tension minus liquid vapor surface tension plus the P puddle which came up into picture. So that is plus PGH plus rho g h squared by 2. And then there was also the element of the hydrostatic head from the previous case. So you'd see that there would be a PG minus PGH coming into picture there as well. So if you see this, and all of this, obviously when you do a force balance, all of this should be equal to 0. So you'll see that these two get cancelled, and all you'll be getting is a very simple equation. So if you look at sigma Sg and sigma Sl, if I use the contact line formula, then I'll be getting something like sigma Lv cos theta e minus sigma Lv plus rho g h squared by 2, equal to 0. Okay, so if I take the reason I'm doing this is I want to find out what is h. So if I bring all the h squared terms, you will see the h squared terms being like this. H squared is equal to 2 sigma Lv divided by something like rho g 1 minus cos theta e. Okay, now if you see this, this becomes h is equal to, you will get square root of sigma Lv divided by rho g, square root of 1 minus cos theta e. I mean, there is a reason why I split these two things up. If you look at this particular term, this has a unit of Newton per meter divided by kg per meter cube multiplied by meter squared per second. If you see this has a unit of square root of meter squared, which has a unit of meter. This is the capillary length. Okay, this is the capillary length, and it is typically represented as LC. So for a puddle, the simplest, if for a puddle, one can say that the maximum height of the puddle is corresponding to the capillary length, because it's the balance between surface tension and gravity. This can be corrected because of contact angle.
So this force balance is written for half of the puddle?
Yeah, half of the puddle.
And then PGH is when you integrate it
over the entire thing. Okay, now you see this, you would get the height, I'm just going to write it here. So you would get this height of the puddle as LC square root of 2 into 1 minus cos theta e. So very simply, if someone asks you the question, I have a low contact angle fluid, and I've poured it on the surface which has an equilibrium contact angle of so and so, what is the height of the puddle? That is the answer. Okay, so it is basically dependent on the capillary length corrected by some factor corresponding to the contact angle. So we don't have to do anything. So it's a very quick way of estimating the height of the film, especially. Okay, and we use this constantly in various things as a first guess of what the answer could be. Okay, so this is one of the elements which I wanted to explain regarding capillary length. So when we look at droplet shapes, we looked at spheres. We looked at the sphere that gave us the Laplace pressure. We also looked at these surfaces where you have a Delaunay surface, which is like a neck. We also briefly discussed about a ligament. Okay, we also briefly discussed about a ligament. And now, of course, this is a different case where you are sitting on a puddle. You're looking at a puddle, and we are finding out what is the height of the droplet. Okay, and all of these cases have got their specific interpretations, especially when if they are in contact with the surface. You will have the effect of contact angle coming up in these cases. In other cases, you wouldn't see that at all, obviously. Okay, so what I'm going to do now is, okay, so this is exactly what I mentioned. So we have the capillary pressure, we have the capillary length. So these are two important things. Now, capillary length it's a very useful parameter. It tells you the one interpretation is it tells you the maximum size of a droplet for it to be starting to be affected by the gravity. But actually that's not true. It is our physics which tells you that approximately if you have a size of the droplet, that will be affected by gravity. The way you test it, the way you test these things is by taking into account, say that if you have a surface, you have a droplet, okay, and then what you do is completely invert it. So you got a pendant droplet. Okay. Now, if the diameter of the droplet is less than the LC, we just assume that it is not affected by gravity. Actually, it is incorrect. It is affected by gravity. It may be affected by gravity in more ways than none. In fact, when we do evaporation, we find there is a lot of we don't use capillary length as a kind of a immediate cutoff between what is affected by gravity and what is not affected by gravity. In fact, when you have a pendant droplet like this, we find that the vapor, if the vapor is denser than the surrounding fluid, the vapor actually goes in this way, okay, as the droplet evaporates. And there is a recirculation zone which is set up in the droplet, which will not be possible if you didn't have gravity, even if the droplet is much smaller than the capillary length. Okay, so there are special considerations where you look at. So, but as a ballpark estimate, what we say is if the droplet size is less than the capillary length, then it is plausible that it is less affected by gravity. Okay, but if you have a extremely small droplet, when you go into nano droplets, of course, you can imagine that they are hardly affected by gravity. But in the range of mesoscale droplets, you still have these questions to be answered. Okay, so this is what we looked at. We looked at the spherical caps as well as Delaunay surfaces. But obviously, when you don't have gravity, you will have surfaces which have supposedly mean curvature. Okay, and that's what you find in experiments in space and all that stuff. Okay, so very quickly, so what we have done so far is absolute fundamentals of capillarity and wetting, and understanding the forces that are involved that take part in the so-called contact line physics to develop the shape of the droplet or whatever it is. Okay. Now, what we're going to do is we're going to go to the next step is how do we alter the the mechanisms of wetting. Okay, and there are various ways of doing it. Okay, there are various ways. Here I've listed about 9 ways, but there are other ways as well. Okay, so one of the typical ways, these are the most typical ways what people do. You can introduce another component, which is a surfactant or a particle. Okay, you can use another. What I have not mentioned is you can use another volatile component as well. That changes the surface tension completely. So you've got additional fluids. Obviously, you can change the substrate. You can maintain the roughness of the substrate, but you can have chemical patterning. Okay, so you can maintain the topography of the substrate. Physically, it looks almost smooth, but chemically, it is altered. Okay, so you can have chemical patterning. You can have topological. This is the most common ways, the topological patterning. You can change the surface patterns and see how you can modify the surface. Most recently, people are using liquid-infused surfaces. So you've got these surfaces which are solids, but you've got these pillars where they inject fluid there. And so what usually happens is they put some sort of an oil. Okay, so essentially, when you deposit an aqueous droplet, the oil, obviously, oil will repel the aqueous droplet, so it's going to sit on the film, but then it's also going to climb on the aqueous droplet. So you'll have all these phenomena happening, and it has its own advantages as well. Okay, so you've got liquid-infused surfaces. You obviously can alter the wettability just by means of electric or magnetic fields. Okay, that changes surface tension dramatically. Obviously, the other cases which we are going to discuss further on is by use of heat. Okay, so the moment you have heat to it, you will have the contact angle changes. And this is one of the ongoing questions. How does contact angle change with temperature? It's an open-ended question, actually. Okay, so that is something. So adding thermal. So this is the surface feature where you have a lead-in frost effect. You can have a vapor layer, and your droplet is sitting on that. The other one is vapor interaction. So you have these multiple droplets sitting all over the place, but then the vapor is actually the vapor composition is actually describing the motion of these droplets. So it has nothing to do with the substrate, it's the vapor. Okay, that also has been implemented. So that's a Solital Marangoni effect. Okay, and of course you can change the shape and the geometry again. The other new thing which people are doing is change the elasticity of the substrate. So you can change. So you can have a pattern substrate. You can have a pattern substrate where one side is more, you can have a checkered pattern where the checks are less elastic than the less. So you have all these kinds of different phenomena, all these different types of you will have a distribution of elasticity over the substrate, and that can change the wettability. Okay, and also the substrate shape as well. So you can use droplets to actually alter the shape of the substrates. Okay, so that is something which we do. So if we very quickly look at the use of surfactants, so surfactants typically lower surface tension. In fact, in my previous avatar, before I did my PhD, I used to work with Hindustan Lever, and I was in detergent section. And detergents, everything has to do with surfactants. And you've got, you name it, 1,000 surfactant, 1,000 types of surfactant. Of course, you have 3 types. But then you've got different types of it. And each one is chemically different than the other. And each one has a different effect on how it behaves. Okay? If you have a detergent based on linear alkyl benzene sulfonic acid, it's very much different than another non-ionic surfactant. The way it interacts. The principles are the same. It will lower the surface tension, but the way it acts, it can be different. The way the adsorption behavior happens is different. Okay, so typically, if you indicate, so if you add surfactant, you can lower the surface tension, and you can see that the contact angle also can drop. But it's not very straightforward as well, because if you have a pure droplet, and if you have a CTAB is one of the surfactants, but if you have a surfactant-laden droplets, surfactants are very strange things. They can introduce their own stress. They can actually cause the interface to be more elastic. Okay, so and they also have their own adsorption phenomena on the surface. So the physics might be different, Plus, they also alter the way the precursor film behaves. So it's not very straightforward on how, in bulk property wise, yes, it lowers the surface tension, but in terms of contact line physics, it's quite complex. Okay? We can't just rely on this figure to say that this is how it's going to behave. Okay? That's the crux of the surfactants, the bit of surfactants. I mean, here is some sort of further explanation of what happens, because surfactants, they roll up these you've got a hydrophobic end and you've got a hydrophilic end. You've got this oleophilic end, and then you've got the hydrophobic end as well. So basically, what is going to happen is the way they interact is surfactants look for emulsification. Okay, they detach the soil. They can therefore create these concentration gradients within the system they are in. Now, whenever you have a concentration gradient in a system of droplets, that can induce solutal Marangoni effect, not thermal Marangoni. So if you look at, typically if you have surface tension with respect to temperature, typically for most fluids, for most pure fluids, it's a straight line, and basically the coefficient of the slope is determined by the thermal Marangoni constant. Okay. In some cases, so for example, if you have a water butanol system, this is a mixture again, your surface tension and temperature profiles are slightly different. It's actually a parabolic system. So there is a region of minimum surface tension, and then it tends to climb back. So these are called self-rewetting fluids. So these are not fully surfactants, but they are surfactant-like fluids. But they are not surfactants chemically. No, they don't have these two different tails and all anything. But once you have a surfactant medium, what's going to happen is you will have the distribution of these surfactant molecules all over the place, and this is highly non-uniform. So if you have a non-uniform distribution of surfactant molecules, the surface tension will change accordingly. Typically, with surface tension with respect to concentration, it can also form, with respect to surfactants, it probably also forms a straight line. Of course, for a simple surfactant, it can form a straight line. But, so which means that if you have a region where you have high concentration of surfactants, and if you have a region where you have low surface, you will have a solutal Marangoni setup. Okay, you will have a solutal Marangoni setup, and the way it acts is again different. And usually what happens is if there's a Marangoni flow, it starts to populate one end of the side. Again, it's like a spring. This becomes more stronger than the other, so it keeps pulling each and every one like this. Okay, that's because, and it will stop only when the concentration is uniform. Okay, so that's how surfactants. So surfactants are pretty complex in the way they act with on surfaces. Okay, of course you can have all kinds of surfactants, and this is that. The other thing that people use to alter wettability is use particles. Okay, liquid marbles are some things which people use. Okay, so typically if you have particles, so basically this is one of the statement by Pliny. So droplets on a surface of water, dust on the surface of a water droplet increases the hydrophobicity. So if you look at this, this is one of the experiments in Edinburgh complex fluids groups. So you can see that this is a water droplet. I think this is a water droplet hitting sand. Okay, so as it splashes onto sand, there is a lot of imbibition. There's a lot of stuff going on. It picks up a lot of particles, and then it becomes a kind of a ball laden with particles only on the surface. There are no particles on the bulb. It's just attached to the surface. So technically, these particles also behave in some sort of a surfactant as well. But they're not fully surfactant-like. Chemically, they're not surfactants at all. Okay? So this is another way of altering wettability, which is using particles. And this is very much used in terms of pharmaceutical manufacturing and things like that. Okay? Obviously, if you look at nature itself, you can see that many of these animals, even elephants, they use just dust to clean up their bodies. Okay, so non-washing without water. It's a dry, it's a dry cleaning stuff. So, so this is, and they use it to remove oils from their body. Okay, so definitely particles do play a role of altering the wettability of the system. This is obviously a very common way. So you can see that you can have chemical patterning as well. Depending upon the shape and the size of the pattern, the nature of wettability will change. Okay, so you can have, so in this case it's a corrugated substrate, but this is here more of a concentric kind of an arrangement here. Okay, so if you look at this, you will have, one can estimate the so-called contact line conditions based on the amount of fraction which is considered to be wetted, the amount of fraction considered to be wetted in a certain pattern with a certain chemical patterning, and the other one is F2 is probably the white region. Okay, so this is how you can actually look at different states at which a droplet can sit on such surfaces. And obviously you must be familiar with, I'm not going to go through this, I'm going to show you one picture. This is probably a more common picture for you to see, wherein you have a suspended state where the droplet is sitting on this pattern surface. This is obviously an exaggerated cartoon here. So when you're in a suspended state, you're basically the pillars that are supporting your droplet, not exactly supporting, but yeah, the pillars, it's just resting on the pillars, and you've got an air, you've got a vapor medium which is sitting around here. So basically this is the Cassie-Baxter state, and obviously at some point this is going to get slumped onto the substrate, and that is the Wenzel state. And obviously if you want to make sure that you want to have a very mobile system, you want to be there, because this guy can easily roll off this guy, but once it is entrenched into the droplet, obviously its motion is completely restricted. Okay, so wetting on ref surfaces, so you can have the Cassie-Baxter state or a more of a collapsed Wenzel state as well. And one can imagine that, as I mentioned, there's no such thing as an equilibrium contact angle here. It's quite a complex thing. So here we put some estimates in this way. So we can say for a Cassie-Baxter system, it completely depends upon the solid fraction. Okay, and this is probably the way one can estimate the so-called contact angle when it is sitting on a Cassie-Baxter system. If you have a Wenzel system, it's again totally dependent upon the roughness. Okay, and this is one of the formulas that one of the approximate ways one can determine, oh, what is the contact angle of this substrate?
So what is FTS?
A solid fraction. So area covered by the solid. So basically these bits are not covered by the solid at all, but these bits are. So it's the extent of fraction. Okay, so obviously you can have all. So in the same is over here as well, where F1 and F2 are different chemical / solid fractions. Okay, and you can estimate some sort of a contact angle based on the fractions involved. Okay. Before I move on, do you have any further questions? Any further questions? So obviously, in the next few lectures, we are not going to do much about. I'm just going to show how patterning can influence this. So obviously, one of the things nature does is you have these bees. You've got these beetles which can trap water within their bodies, so that they can use it during the summer or dry areas or during the daytime. Okay, and that's because of the patterning on their substrate, on their skin. Okay, and obviously many of you are doing microfluidics, so it has a lot of applications there. Nowadays we look at microfluidic reactors where wettability is important. We want to do chemical reactions within a small droplet, so that you have micro manufacturing of stuff there. Obviously, this is a very common way, topographical patterning, be it with lotus leaves or whatever it is. And one of the ways to replicate that, and many research groups are trying to replicate what a lotus leaf does, but they've not really gotten there. That's because the lotus leaf is pretty unique, and because it has micro roughness as well. and not just kind of a spiky thing there. Okay, so so this is what we have gone through anyway. So this is just I hope it plays, yeah. So this is a lotus leaf. So you can see that you've got micro roughness and you've got a macro roughness. It's very difficult to represent the micro roughness. So people have done MD simulations and all that to understand what is it more. But you can see that it completely rolls down the surface. And one of the possible reasons, one of the possible evolutionary reasons could be that it was to take off debris from the lotus leaf, so that it is as clean as possible all the time. Okay, so that's obviously the super hydrophobic surface there. And again, people have looked into various patterning methods as well as patterning configurations. So you can see that people have put posts. David Carey himself was doing a lot of posts as well. They were not very successful, though. They themselves say that they're not fully successful in this. People have done parallel grooves to replicate rice leaves. People also have done butterfly wings because they're pretty hydrophobic, but at the same time they've got layers on top of each other. Okay. One of the things that nature that some of these living creatures have used their surfaces because of the nature of because of the surface structure they have, and because of the wettability changes they have within the over their own entire skin, they can use it to actually breathe. Okay, so in fact, there are some places where a part of the skin is more adapted for oxygen takeover. The other part of the skin is more adapted to release CO2. And that is completely governed by the wettability, the amount of wetting it can happen. Okay, and basically the porosity of the system as well. So you've got these complex micro and nano structures. You can see that I'm not an experimentalist. I'm struggling to explain all these things. But what you can see is clearly is when you look at these structures, you've got these pillar-like structures, but then you've got these valleys, and these valleys are the ones where you need to take care a lot, because if you want to make sure that it's hydrophobic, you need to encourage a Cassie-Baxter state. You should discourage a Wenzel state, so that you don't get trapping of liquid or anything, and that's a major challenge. Okay. Again, people have looked at different designs and optimized them. So you can see that these are simple posts. These are basically having a kind of a cap on top of it. These are basically hats, kind of a structure. And the way the liquid creates these, sits on them is quite different as well. Here you can see that it just spins the edges, and edge to edge there is a contact here. Here again there is an edge to edge, but it's connecting not to the edge of the pillar, but it's the edge of the T, which is contacted. But then if you have this kind of an umbrella shape, these two guys are contacted. The umbrellas are basically the ones which are actually pinning the interface. And obviously one of the things people want to check is if this is a Cassie-Baxter system, when does it break down? At what point does it fail, okay, to form a Wenzel state? So you can either have a base, you can have a failure at this point, or you can have another failure somewhere else. So that is one active area of research. So people look at where exactly things can fail and how to optimize this better. So the key important properties, or the key properties to make sure that you have a proper surface, depending upon your application, is number one, your contact angle hysteresis. Okay, what are the pinning forces that must be overcome for it to remain in that state? The other thing is, what is the critical pressure? What is the pressure? What is the maximum pressure it can withstand before it starts collapsing? Okay, before whether it can have a edge failure or whether it can have a base failure. I'm going to come to that shortly. Okay, and then just by virtue of the arguments which we just posed, you can actually calculate what is the ballpark minimum energy required. Okay, what is the ballpark minimum energy barrier or minimum energy required for the failure from a suspended state to collapse state? Okay, so with all these things in mind, can we actually design a surface? Can we actually design a surface based on the needs of your application? Okay, people have done a lot of work on this. So people have done a lot of work. So the color coding here is based on contact angle hysteresis. The color coding is based on the contact angle hysteresis. And if you see these dots, you see these purple dots here. The purple dots is where is the types of failure. So basically, you can have for it to deepen, for it to go from a suspended state to a completely deepened state, you can either have a bridge deepening. That is the gray dot. So the gray dots are somewhere here. Okay, so that's where a bridge will completely deepen, and so you have a deepening from this, from not the leading end, the rear end of the T, and it then comes off. The other thing is edge deepening. Edge deepening is when it comes off directly from the top of the T. Okay, from the top of the T, that is the red dots. So this is the range where you have deepening occurring from the edge. The other one is lip deepening. So lip deepening is at this particular portion of the T, okay? And it just pulls off from there, okay? And that is lip deepening. So this is the region. So this is, and here obviously you've got the geometry depth. This is the area fraction and the lip depth. That is the depth of the T. And basically there will obviously be a region where you cannot deepen at all. You will always have a Wenzel system. You will always have a trapped system, and this is non-deepening state. And non-deepening state are these here in these sections. So non-deepening states, and then obviously you can have all kinds of combinations. So what they call it as hybrid deepening in this region. So depending upon, so one can design your pillars. One can design your pillar shapes based on these experiments, and these are completely experimentally driven. Okay, these are not done through modeling, and of course people do energy analysis to check if this is true, but obviously the energy analysis can only do that much because we don't have the complete physics there. Okay, so you can also have, so people also have optimized these models. People say that, oh, this is the most optimum case, but again, it's so fluid dependent as well. Okay, so there is a lot of experimentation that is done when you check the geometry of the pillars. Okay, this is again this is the failure at which, this is the type of failures which we look into. So if you have a very flat or a short pillar, you will have a failure which is occurring from the edge of, from the bottom actually. So that is when it starts deepening from there. So that, what we call that is a base failure. The other one which is there for tall pillars is from the cap. So it's right from here, it's going to deepen. So we look at these systems from both these ways. At what point will you have a cap failure, and at what point will you have a base failure? And if you look at this, you would have, if you map out the whole thing, there is a very nice zone. And this is basically the optimum zone where you're probably the safest. Okay, you're probably the safest. So if you look at, so if you decide to have a pillar height of 0.2 and an area, so the corresponding to that, the area fraction would be about 0.1.
These are simulation systems or
experiments, completely. Okay, these are experiments, completely experiments, and the color over here is the pressure, the amount of force that you need to deepen. Okay, so obviously people do these experiments by vibrations and all kinds of other things. Okay. Okay, so this is what we have seen. So basically, one of the key results is there that base failure. If you want to have a base failure, the base failure critical pressure increases as height increases, because as height increases, you won't have a base failure anymore. You will have a cap failure. But the problem with cap failure is that it can happen at any height. Okay, It's because it's ultimately dependent upon this region, completely there. So I need to just look at the reference there. I think it's in the order of millimeters. But most of the time this is non-dimensional because this is, I think they normally non-dimensionalize this with respect to the system height, whatever they're considering. So,
And the contact angle wouldn't
yeah, it would definitely come into picture, but this is the minimum most, again, that's why I said it's so fluid dependent and it's so material dependent. So yes, it is contact angle dependent. But when you look at failure, it's more likely that there's a geometrical effect. Yeah. So this is again some sort of a kind of a path coordinate for failure mechanisms. So typically you can have, so as I mentioned, you can have a base contact, or you can have a cap contact, that's where you have. Okay, so if you basically, if you're in a suspended state, you're not in the minimum energy zone, but you are in the Cassie-Baxter zone, which is almost stable, not really stable. It can go into Wenzel very quickly. So this is at a higher energy level than the complete collapse state, that is Wenzel. Okay, and basically as it moves from suspended to collapse state, it passes through this energy barrier. And that energy barrier can be obtained, can be just through your processes, can be just through the vibrations of your system, can be through your, it could just be because of the way the chemistry of the substrate itself is. That has supplied its enough energy. Okay, so that's why people have to be very careful in designing these substrates, depending upon the application they're interested in. Obviously, there are several applications. People have used it for water purification. People also have used these things for, optimize these geometries for various substrates. But again, they actually use the failure parameters to have an antagonistic optimization, depending upon the application. So obviously, there are three things that you look at. You look at the hysteresis, you look at, this is where your contact angle comes into picture. But again, you'll be looking at critical pressure and a minimum energy barrier, especially when you have a T-shaped pillar. So obviously, if you couple all these things together, you may be better off in optimizing your surface better. Okay? But these are the key physics that have to come into picture to develop a better substrate. Okay, so again, if you increase your cap width, you're more dependent upon, as you keep increasing your width of the cap, contact angle properties become very important. If you decrease the system scale, you shift from critical pressure as a major problem area to a minimum energy barrier. Okay, so if you decrease the system scale, if you go to smaller and smaller systems, critical pressure becomes less of a problem. It's basically the substrate energy which becomes more of a problem. And you want to make sure that you work against it if you want to have a Cassie-Baxter state. Okay? So all of these three parameters must be looked into when you want to consider optimization of a surface. Okay? So this is one example. We did a lot of modeling for this particular example. Is you've got certain patterning there, and you've got another set of patterning there. And what we wanted to see was how the droplet can move. So it was basically enabling motion of the droplet. It's for self-cleaning substrates. Okay, so it's for self-cleaning substrates. So if you deposits there, it goes into the region which has another level of patterning, and there is more propensity towards. And the idea of this particular paper was to improve this velocity. So he tested a number of patterning geometries to see if you ever increase the velocity, or if we can increase the velocity. Okay. Yeah, so there are some things which I mentioned here about optimizing geometry. But again, the key parameters, I think, is is critical pressure, energy barrier, and contact angle hysteresis. I think I don't need to mention too much about that. Do we have any questions before we go ahead? Yes?
So is there any specific way how we can make these T patterns over the...
Yes, there's a lot of literature on that. So it can be, I'm not an experimentalist, you can probably tell.
You need to do some depositions, then etching, wet etching, you can keep that.
The CVD.
CVD.
But then all these methods have got an issue that once you do the experiment, they get degraded. The durability. Durability is a problem.
And also like the exact edge is not possible. Usually undercuts and U-shape is formed in these things.
Yeah. So, and durability is a big issue with these surface patterning. That's why people do these over several weeks and sometimes even hours. It gets degraded very fast. So there's a lot of work in terms of in terms of this. I'm not going to go into wicking in particular because wicking mainly is kind of imbibition and things like that. I'm not going to go much into that. But what I have done, I mean, you can see the notes yourself. What I have done here is I've tried to bring together the energy physics just by looking at the pattern of the substrate. Okay? I don't need to go into depth, but it's again based on totally on the geometry parameters, nothing else. So basically, it's energy minimization, looking at the energy of the substrate based on the surface geometry. I define a certain fraction, I define a certain roughness, and based on that, I calculate. And from here, then you can calculate the so-called contact angle from here. Expected contact angle, I would say. Okay? But very quickly, I would say that if you have a pattern substrate in this fashion, your contact angle is fundamentally dependent upon the roughness and the solid fraction. That's it. And very simply, we get something like 1 minus f by r minus f. Okay. Obviously, just like we have super hydrophobic surfaces, we also have super hydrophilic surfaces where you want to have complete wetting. That's also a very difficult thing to do. So here, people sometimes use roughness to make it more wetted. Okay, it's the other way around as well. So you can actually see this reference where they actually exploit roughness to expand the spreadability of the liquid. Okay. This is again liquid infused surfaces. This is basically a pitcher plant. So you can see that this is a dried pitcher plant. A dry pitcher plant ants move very nicely, but then there is a wet pitcher plant, and the wet pitcher plant has got this mucus layer, which does not allow this thing to pass. So everything falls into that. So basically, when you have a liquid infused surface, you have this patterned substrate where there is an oil which is infused, and as soon as you deposit water, it will form a kind of a liquid lens. And the liquid lens, and sometimes the oil, based on the surface tension, it can actually climb on the water droplet as well, forming that. Sometimes it's of great use to have it, but sometimes the problem with slip surfaces is that durability. How long can the oil remain in that way? Because ultimately, sometimes it's going to go. Okay. This is again some example. You got Teflon and a hydrophobic surface and a liquid infused surface. You can see the idea is to develop a hydrophobic surface, but if you look at LIS, the liquid infused surface does pretty good job of it, but the main problem is durability. The main problem is durability. Yeah. Again, this is a very good example of where slips can be used. This is for preventing food waste. So essentially, making sure that you can empty out everything that you can from a bottle. You can also use it in cleaning surfaces. You can make it as a slips treated surface can be said to be self-cleaning up to some extent. But again, durability is always a question. How long can it last? Okay, and here is some of the process which does. So you got Sarthak would tell you better than me. You can have this structuring there, and then you got this functionalized, and then you infiltrate the lubricant, and you wait for the lubricant to settle down, and then you can do whatever you want with it. But again, the problem is how long will it last? Yeah, so we were talking about carbon capture during lunch. It has also been, LIS has been tested for carbon capture. Okay, they've been used on membranes, water purification membranes. They've been used on membranes of all kinds, actually. They've been used on adsorption membranes as well for carbon capture. The other thing you can do is you can look at liquid and nanoparticle interaction as well. Okay, this is basically you can see that it's you got this nanoparticle coating and you got a liquid which is impregnating on that. That is another way of creating slip surfaces. But again, the questions of durability always remain. So you can have this is a normal surface, which is a bare surface. But then if you have a kind of a gradient of wetting there, if you have a gradient of wetting based on your slip surface, you can make the droplet move by themselves. But again, the problem is because it's a slip surface, as the droplet moves, it picks up some oil along with it. So you're actually depleting the oil as it goes on. But these are things which are under development. So obviously this would be liquid shaped, liquid infused surfaces are probably future for some things, may not be all. Again, electric field. Electric field is great. You can see that if you don't have an electric field, you have a droplet which has a certain contact angle. But the moment you impose an electric field, it just changes its shape. It can have a higher contact angle or whatever it is. Okay, and obviously this is dependent upon the electrical force that you give, and typical relation that we use when you have an imposition of an electric field is this. So the new contact angle is dependent upon the dielectric constant and things like that. Okay. Again, where are these used? Obviously, all of our LCD screens, they're used extensively there. They're also used in liquid lenses. I was involved in a project which required. This was actually. This is a fun project wherein there was an oil spill on a sea surface or something, and they tried to put two plates to it, to just a test, to see if you can segregate the film a bit more from the seawater, or to make sure that it gets attracted to one side, and it works. But of course, you can't have such a big plate. But this is just a fun project to check if electrical field can actually change the dynamics of surface tension on a liquid lens. Okay. This is obviously very common, the lead-in frost effect. So obviously, as you boil beyond the boiling point, as you go beyond the boiling point, very much more beyond the boiling point, you actually have a vapor layer on which your droplet can sit. And the droplet can move, based on the vapor velocity there. So in this case, this is from my colleague Gary Wells. So if you have a very high temperature surface and he deposits a water droplet, it evaporates and it gets suspended, it just starts moving. But then if you change the structure of the substrate, it's going to do interesting things. So if you have a ratcheted substrate, it allows it to move. And if you put the ratchet into a circle, it actually becomes a kind of an engine. And people, what they have done is they have put it on a metal plate and they generated small amount of electricity out of it. But again, this is just a test. And this is on a block of dry ice. So it was, it was successful. It was just a proof of principle. Okay. This is where it is going on. Yeah. Obviously, the shape of the substrate can affect the dynamics of contact lines. So this is from Prakash. So you can see that if you want to make sure your droplets can move, if you shape your substrates in a certain way, that can actually propel it farther. So this is a very simple example of that, the way the ducks do their business. The other thing is obviously elasticity. I think of all the methods from slips, etc., this is probably the more physical one. This is possibly the more accessible one. And this is probably the more durable one. Okay? So if you have a soft material, that can actually influence the way the droplets can behave. So here, by virtue of changing the elasticity, you can actually make sure that the droplets can attract each other or repel each other just by changing the nature of elasticity. Okay. There is another example which I would like to show. This one is a droplet which is sitting on an elastic surface, and it's basically, as it evaporates, it actually folds the surface. So it's capillary origami. Okay. So people can. So this was one of my own students. She did that. Obviously, you can look at these aspects. So we looked at the Delaunay surface, and this is how it can alter if you have a kind of a elastic membrane rather than a metal surface. This is things which we're going to talk about further on as well. So this is the influence of vapor field. This is very interesting because here you have different types of droplets, different compositions of droplets actually. Each color is a different composition, and you can see that these guys are chasing each other. Some of them are chasing each other, some of them are attracting each other, and so on. And that is completely influenced by the vapor field around it. I'm also going to show you how it happens. So there is another video. So you got this droplet, and it's getting pushed by the vapor, and some of these are highly volatile. Okay? So as the droplet moves, it can get pushed based on different volatilities of each thing. Okay. The other one here is these are two droplets, and this particular experiment is based on salt. So one of them has got lithium bromide, which is used in dehumidification and humidification stuff. Okay. One of them is rich in lithium bromide. The other one is pure water. Okay. I'm going to repeat that video again. Yeah. So this is rich in lithium bromide. This is pure water, and it is actually absorbing water off through vapor. Yes.
What was the surrounding medium? Was it like
Atmosphere. Just like this. Just keep, yeah. Atmosphere. Probably it was in a cage, but it was in a box, but nothing special.
Lithium bromide drop is like absorbing the surrounding.
Yeah.
Smaller water.
Yeah. So this is pure water. This is lithium bromide plus water, maybe. And basically, it's just absorbing. So we did the modeling of that as well. It's published in GFM. So it's there. So there is a competition between evaporation and absorption in those cases. Even if you heat it up, it won't get evaporated. There's a fight between the two. Okay. So it's absorbing. So this is one pure evidence of how vapor field can affect the droplets. So just to quickly summarize, so obviously you can see that you have a wealth of phenomena in terms of wetting, and you can do all kinds of games with it based on whether it's substrate, whether it is the liquids, whether it is the atmosphere, whether it's the precursor film, whatever. You can play all kinds of games with it. But ultimately, the question that you may need to ask is, what is your application and where is it going to be beneficial? Okay. Any questions? Oh, good, very, very good question. So we found that So if it's a function of radius, I'm going to tell you, I think it is, if the radius of the droplet is r, I think they should be less than 3r apart, okay, for them to really feel each other. But then this is only for 2 droplets. But if you have multiple droplets, then I don't know. Because when you have a population of droplets, they can act as a single entity as well. There's vapor shielding. I'm going to talk about that later, but yeah.
So there can be much complicated like evaporation.
Yes. Yeah. So if you have a population of droplets, for example, I mean, if you do breath figures, so if you just breathe on a mirror, you'll find these multiple, you have about maybe 5,000 droplets there. But then if some of them, if you can imagine that you have a distribution of absorbent droplets and the non-absorbent droplets, then what happens is the non-absorbent droplets can develop a vapor film and it can shield the others from getting absorbed as well. So you can have these effects which can occur. Yeah. So this is for 2 droplets here, it's very simple. Yeah. Good, I think we are nearly done. We're done actually. We have tea?
So now I invite you all for the tea.